All right. So, studio audience tonight. This is our last episode. It's episode 11, but it's our last Zoom. Yay. Okay. Hey, Sophia's back. Welcome back from Colorado, Sophia. So, this is the last recorded episode. We'll meet on. Here's what we're talking about tonight. That's a full agenda. I was telling. Go up to 4 now. I was telling the guys that were here that this may go over because it's my last one. I can't say we'll talk about it next time, but if it goes over, just you can drop off at 7:30. I may go all the way to 7:45 or so because I want to at least touch on all these things, not necessarily in this order. I've changed the order since. I also told them that about 4 hours ago the whole thing just disappeared, and it's never happened before. And explain everything, can't explain it yet. So they're still looking at it. All right. This is what we're going to talk about. So let's start talking about Thursday. This Thursday, it's not going to be tomorrow. We're not, the original thing had it tomorrow, but because my Florida trip got pushed back, I'm not leaving until Friday or Saturday now. So Thursday is a better day for me anyway, probably a better day for you. Thursday at lunch is what we've decided. And I went ahead and just made the executive decision and picked Hideaway Pizza at noon, Hideaway Pizza. So we're not skimming here. This is the good stuff. So Hideaway Pizza at noon on Thursday on Campus Corner. Now, thumbs up if you can make that. Thumbs up if you can make Thursday at noon. Jacob. All right, so JS. Jacob and I will be eating lots of pizza. Just Jacob and I. Nobody else. Nobody else for pizza. Okay, you guys can't make it, or would another time be better? Would 11 a.m. be better? Would 1 p.m. be better? Is it a problem with, I don't have the chat open. Let me open the chat. Anthony's not sure. I think I can. 12:15. Well, I just threw out noon. It can be fine. We can make it, let's make it 12:30, okay? 12:30. That works better. If I say 12:30, then Carson can be there, eh? Hey, you guys are going to give up free pizza, are you? So, and Jacob can still go. And Carson, now I'm going to say, is a pretty good possibility for 12:30. Yes. Okay. And Anthony, keep looking at that. If it's involved, if you need a ride or something, I'll pick you up, whatever. But every time I say I'm going to pick up a kid or take a kid home or something, or another teacher, they always end up living out by the lake. So what? I thought you live over there on Brook Street or something. So I don't know, but maybe. I ride your bike, right? So right now there's 3 of us. Sophia says no on that. I'll talk to the other people, and it's really hard. I know it's really hard to get 11 people together at the same time. The reason why I want you there is, I'm going to feed you some pizza and I'll give you your certificates and we'll have a good old laugh. But also, I have a form. I want you to fill out some questions, and I can send them to you, but I'd like to, right there with pencil and paper, you fill them out before you leave, okay? And it's just kind of an exit poll, how are we doing? What can we do better? What you like, what you dislike? All right, so pizza. Someone showed up here. Let's see who we got. Okay, Matt. Now, Matt, we're doing a poll here. Who can go eat pizza Thursday at 12:30? Thursday at 12:30 at the Hideaway. Free pizza for you. I said bring a dessert, but don't worry about bringing a dessert. Just show up. Pizza, and I'll pick up the tab. Okay, pizza. So Matthew, is that something you can do? Still thinking. Thumbs up if you say yes. you can handle that. Well, think about it. Maybe you're waiting on a ride or something. But, all right. We'll talk. I may be sending you emails. You guys got to actually answer your emails, okay? I do a group meet, but we don't have one. I don't know your phone numbers. So here we go. Some of you do. Now, on the reference pages, I wanted those. There's now 36 reference sheets. In May, we had 20. We're up to 36, which is cool. A lot of stuff we skimmed over, but it's in there because I just went ahead and downloaded everything today. But I thought this needs to be, the problem with it is it's like, it's like images. And so you can't, like, if you want to look up something, say you want to find the quick formula for the blue quad, and then you have to search. So I thought, well, I'll make it searchable. So now all of those have, at least like above, it has the name, what's in that sheet 1, what's in sheet 2, what's in sheet 3. So if at the top of the ASCII's physics show, and you on the search, you searched, orange kinematic equations, it'll take you to anything that involve it. It'll also take you to the reference sheet. Okay. So that's a nice addition, I think. All right. So it is Monday. We're going to do a quick one though today, because I got too much to cover. So I've got to stop the sharing here. I've got to stop recording for copyright issues. Okay, so for those that are watching the video, we'll cut out for a second, then we'll come back. All right. Yeah, I love Phil Hartman. His wife shot him dead. Crazy. She was cool, turns out. All right, so now let me, that was years ago. But he was a Saturday Night Live guy, and you'd recognize his voices, because a lot of voices for Simpsons and stuff. He did. All right, so here we go. All right, recording again. First thing we're going to do, we're going to hit a lot of little topics tonight, and then we're going to go more in depth on torque. Okay, so I've mentioned power a couple times. So very briefly, if we just never seem to work out where we could run stadium steps. We should have, when we went to those field trips, we should have done some timing then, but I didn't think about it. So you run, like in class, I have them run stadium steps, and we time ourselves. We measure how much each step is. We are working against, it's like we're working against gravity. So gravity's doing negative work on us. We're having to do positive work to get up the stairs. Work divided by time is power. So the whole point to running up the stadium steps is we're trying to be stronger than a horse. And last year or 2 years ago, I made it. I was stronger than a horse. But I think 2.4 horses is the strongest. I think Yemi or Oe or Clay had that honor. I could give trophies out when they did it. But this was the table we'd fill out. That's all the instructions, and there's the table we'd fill out. But basically it just comes down to power is measured in watts. Here's power. Here's a sample problem. This is on slide 29 of your equation sheet. But power is measured in watts or horsepower. We're used to horsepower, but watts is the SI unit, the metric unit. But there's a conversion. 1 horsepower is 746 watts. So a watt, 1 watt is a Newton meter per second. So we know Newton meters is the work. This part is the work. And this part is the time. Okay. So work divided by time. If you did it in horsepower is 550 foot-pounds per second. That's what a typical horse would do. They would tie the horses up, and they would run, the horse would go around and around, or mule, whatever it is, to, over a well. And so that would be the average horse. I don't know who finally said, okay, 550 foot-pounds is the average horse, what they can do per second. So if you can do 550 foot-pounds in a second, you're as strong as a horse, which humans can do it in bursts, like in 2 or 3 second bursts. A horse does it all day, right? That's an average horse all day. So we have a couple of sample problems there for you to look at your leisure with instantaneous and average power. Okay. And then here's another problem involving Niagara Falls. And we spend a day talking about Tesla and Westinghouse and back of the envelope measurements that they were doing to kind of see how much money, because the first hydroelectric dam was at Niagara Falls. And it gave Tesla a chance to show his AC current. One of my books on the Facebook group is called Empires of Light. And it's a story of the electrifying America. Really good book. And I would suggest you read it. It's a good summer read, actually. So it's Edison versus Tesla, basically. But this gave Tesla hooked up with Westinghouse and gave him a chance to show that AC current was superior, which it turned out to be, because DC current didn't go very far. So another way to do power is since work is Newton meter per second, and a Newton, you can break it up into, a Newton is a kilogram meter per second squared, and you can break all those up into the fundamental units. You can rearrange them and you get dm/dt GH for power, the amount of power you get off a waterfall, hydroelectric power. How tall do you want this column of water? Like I say, we spend a whole day just going over that. But here's what the megawatts of power that they determined from the back of the envelope. And Westinghouse is saying cha-ching, and Tesla's going, okay, I finally get to show my stuff. Here's a flow chart: work, energy, and power. This is on your equation sheet, on your reference sheet. All right. So that's power, and power is always like at something we throw in there at the end. Okay, there's, you look at a 1 horsepower motor, and you get a feel for, if I want to lift, how much do I want to lift off the ground? Well, how many pounds is that? How far is it going to go? How quick do I want to lift it? And then from there, you determine what motor you want. Compound machines, since we're talking about motors and machines, we've talked about compound machines. The first one I showed you was a fingernail clipper, right? But when they were redoing they were building at Norman High, they were building, totally redoing it. This is from, I don't have the date here, but this is from a few years ago. And this big old crane was out there. So we went out there one day, and we're counting all the simple machines, what added up to, for this big crane. Well, that you start off over here with the load, that has an IMA of at least 6, ideal mechanical advantage, for that pulley system, those cables and the pulleys, which means that if I pull up with 100 pounds of force, I can theoretically lift 400 pounds, 400-pound weight. But there's more than that. There's a couple of third-class levers, because you need a distance advantage here. You got to be far back from it. And then there's another set of pulleys, a block and tackle set of pulleys right there. And that one we counted 10 ropes or 10 cables. So thing is, you multiply IMAs. So this could have, third class is not going to help your mechanical advantage. It's going to give you a distance advantage, but not nothing else. So still though, 4 times 10 is 40. That means, 10 pounds, you lose probably some of that with the third class lever, maybe half, but still 10 pounds will pick up 200 pounds. 10 pounds of force will pick up 200 pounds. So, and you lose some because of friction and all that too. So I have 4 sheets dedicated to different kinds of machines in this is slide 33. I put the 4 laws of thermo. We'll talk about that in a minute here, but the 4 laws of thermo there. And then on the machines, the one thing we didn't talk about much was wheel and axle. And wheel and axle is kind of like a pulley, but one is small, one is large, one radius is small, one radius is large. So you could get all kinds. You can get distance advantage. You can get force advantage, depending on which one's the wheel, which one's the axle. So you probably use wheel and axle all the time. Every faucet you turn on is a wheel and axle. Your car, your steering wheel is a wheel and axle, right? I mean, you get the big wide steering wheels, the more, and that's where torque comes in, which we're about to talk about as well. Shower handles, everything is wheel and axle. So that is a very important machine. We talked about fingernail clippers. There's, can openers, wine bottle openers, something called a jack screw. A jack screw is an inclined plane, which is basically a screw. A screw is basically an inclined plane wrapped around a nail. And then it's also a wheel and axle. So a jack screw is a compound machine, and you can use it to lift huge amounts. Bicycles full of different kind. All the gearing is one thing, but bicycles full of different kinds of levers. Overall, a bicycle is a third-class lever, but it's got a lot of, because you want a distance advantage, right? You turn in a small circle, your bike goes in a big circle. And the early bikes didn't have gearing, and so it wasn't really very fun. But now they have all the gears, and so you're gearing down, you're gearing up, but ultimately you're trying to make those much wider tires than your sprocket move. And then, of course, any kind of internal combustion engine's got tons of pulleys and rocker arms and everything else. All right, so then I'm going through a couple of compound machines, a couple of examples here. Each of these were on a test, and I would give them a test. I give them this. Let's say, okay, tell me, you have 100 pounds. Tell me how much you got to pull up on the wheel and axle to make this work. And so you go through each one. You start off with a wheel and axle. Then this goes to a second class lever. There's a pivot right there. Then it turns into another wheel and axle. So it's a three simple machines put together to make a compound machine. And in this case, for the 100 pounds, the AMA is 3.6. So it takes about 30 pounds or so to lift that 100 pounds with this crazy lever. The next one here is a little more complicated. This was on a test from a few years ago. And I think in this case, I said, okay, I'm pulling up with 400 Newtons. How much can I lift? And so the weight, the loads down here, I'm pulling sideways on this. It looks like I'm getting a 1, 2, 3, 4 IMA of 4 here, because all those are load bearing. The load of this one is okay, so hold on. We start off with this initial load, and then this is the effort. Well, the effort here goes through this second class lever, and then this becomes the load now. Then that goes into the wheel and axle, and that's the effort. And then this becomes the load right here, and then this is the ultimate effort. So your input force is, say, 400 Newtons, and you go through the whole thing. Overall, it looks like, when I did the math on this, it looks like you can lift 995 Newtons here with 400 Newtons of force. And you go, well, that's not that great, but there's maybe reasons why you have to go through all this, because of spacing or whatever, why you have to go through all these different direction changes and all. Okay, so that's an example of a compound machine. Of course, a Ferrari is a pretty good example. And here I'm talking about where the torque comes in, the connecting rods and the crankshaft, all that involved is basically just all the different levers, okay? Okay. Now, we're just kind of going through and hitting all the things that we didn't have. And everything I'm talking about is a day or 2 or 3 of class. But not much time. Ultimate Fighting Tool, I said we'd at least get to a little bit. Ultimate Fighting Tool comes out of this worksheet. I've added this worksheet. I added like 3 worksheets to the Askey's Physics Show Facebook group. And the key is posted here in case you want to play around with it. The first thing we do on this worksheet is what we did last week, where we derived the work kinetic energy theorem. And then we use that, with the pendulum. I have this huge pendulum I bring in the room, and it goes back and forth, and we put our nose up to it, and we got to close our eyes. And so we waste 25, 30 minutes doing that. But then we get down serious about the pendulum. And we look and see what's doing work. You know, gravity does work on the way down, positive work on the way down. It does negative work on the way back up. It's conservative. We talk about uh, gravitational potential and kinetic energy, how they're both related to each other. And so we say that if you're looking at a system, a simple system, you have UG. UG is a symbol for gravitational potential energy plus Ki, and that's kinetic energy. 1F, as we found last time, it's 1F mv squared, and that equals UGF plus KF. This is a baby. That's a baby ultimate fighting tool. There's only 4 components here. The ultimate fighting tool actually has 9, and I'll show you that in a minute. And you won't get into the ultimate fighting tool until you get to AP physics. And that won't, even then it won't be till second semester. But I'll give you a little preview here in a second. So this worksheet, and I go through there's all of it worked out. But down here, then we get into hydroelectric dams. That same formula I showed you a minute ago, you know, to figure out how many megawatts you get out of that dam. Here's the baby ultimate fighting tool, and then we do a couple of problems involving it. So the ultimate fighting tool, I just made this sheet up this morning, or I finished it. This is side 32. The baby one is the one that we use in physics, in regular physics, and that's what I just showed you. It comes from the first law of thermodynamics, which is conservation of energy, right? EI equals EF. And you can expand that to gravitational potential here, gravitational potential plus kinetic energy equals final gravitational potential plus final kinetic energy. And you always see this with, it's called roller coaster physics, pendulum physics. You know, as it's going up, once it's at the top, the pendulums, they go back and forth. Once you're at the top, you have all gravitational potential. It's not moving, so there's no kinetic energy. As it comes back down, you're starting to move faster, some more kinetic energy, but you're losing gravitational potential because you're not as high. And so it goes back and forth. There's something called the ZPL, which you have to establish. And ZPL means zero potential level. That's all part of working these problems. If you want to expand that, as you will in AP Physics, you have, so you have initial gravitational potential, you have initial kinetic energy, you have initial spring potential. Remember we talked about Hooke's law, negative Kx. Well, if you integrate that, which we'll also talk about tonight, if you integrate that, it ends up being 1/2 Kx squared. That's the antiderivative of negative Kx. And 1/2 Kx squared is the energy you get out of a spring, okay? If you integrate force through position, you get energy. And then there's rotational kinetic energy. That's things rotating, just because things have energy because they're rotating, right? We talk about tides and how the Earth's losing energy because of the friction involved with the tide. Therefore, the Earth slows down because it loses rotational kinetic energy on a large scale. And then all these happen again. I see I made a mistake right there. That should be F. That should be an F. That's final gravitational, final kinetic, final spring, final rotation. And then this last thing is the work done. That's the work done by friction. That's Pac-Man, right? So Pac-Man always eats a little bit. So you got to tack that on. Oh yeah, we lost 10% of our energy to friction. So the ultimate fighting tool, if you go ahead and put the whole thing out, put all the equations in there, you get this. There's gravity, initial gravity, gravitational potential. There's initial kinetic energy. There's the initial spring force or spring energy. There's initial I omega squared. We'll get into that. We will get into that next year, or AP Physics will. I omega squared is initial rotation energy, and then the final, and then the work done by friction. And that usually is some kind of, it's frictional force times the change in position, absolute value. I make it absolute value because I'm tacking it on as an addition. I could subtract it from the left side. Some nice textbooks will do that, but I'm just showing, hey, you have to balance it. You got to say, okay, we got to balance this energy, and some energy was lost to heat. Okay. All right. So that's that sheet. Now let's talk about intervals. I started talking about integrals last time. I'll do a little bit of integrals, and then we're going to spend the rest of the time on torque. Okay, so I don't know how quickly I'll go through this, but turns out last time I thought I made a mistake. I didn't. I was okay. Just the way I worded it, it's kind of weird. So what I'm saying is I have this whole big box of I got this whole big box of blocks here, and I said that what if each one of these blocks is it's 1 Newton high, and it's 1 Newton of force for 1 second. So this is not work I'm looking at. This is impulse. But you could also plot things force versus change in position, and that's work. Force versus change in time, that is impulse. Okay, but they're both integrals. So if I have this, and this then represents the area represents 1 kilogram meter per second, because Newton is a kilogram meter per second squared. Multiply that by seconds, I get a 1 kilogram meter per second, which is the unit of momentum, right? That's change in momentum. So if I were to apply a force for a second, I would do that much change in momentum. If I did it for 2 seconds, I would double it. 3 seconds, 4 seconds, 5 seconds, 6 seconds. Okay, so that's telling me that this is going to give me 6 Newton seconds worth of impulse, which would change a 1 kilogram object by 6 meters a second. It would speed it up by 6 meters a second because it's 6 kilogram meter per second. Okay, no big deal yet. No, that's not integrals. No, that's not integrals. Now let's get to the integrals. So we'll start off easy, then we'll go harder. So now let's show the accumulation of it. Now that's accumulation is a key word here. That's what an integral is. An integral is the accumulation of whatever it is, force, energy, impulse. You're accumulating it either through time or through position. It's either dt or dx, all right? So in this case, we're going to show on that, so that the front row is what I just showed you. That's force of 1 Newton over 6 seconds. The back row is going to show how that force or that momentum is accumulating over those 6 seconds. So initially, we have 1 kilogram meter per second, right? Then if you add to it, we start adding to it. In the second second, now I'm at the 2. In the third second, I'm at 3. So it's a fairly trivial case, but you can see that I'm growing a line. Now this is pixelated, but I'm growing a line. If I connect those up, let's go yellow. If I connect those up, I'm growing a line like this is flat. And we did this back, bad choice. We did this back when we did finger dancing in class. The first one's flat, and so you go look at the flat, and then that tells you that the next one's, if the bottom one's flat, the second one's linear. And so because the second one's showing that linear accumulation of change in momentum. Okay, so then the fifth one, okay, et cetera. So we get to the end and we say, okay, this force acting over those 6 seconds, this constant force, which is represented by this one, okay, this constant force acting over those 6 seconds, this shows the accumulation of, and notice the accumulation is not all the blocks put together, it's only the last one. So it shows the accumulation of those 6 blocks. Here I have a block, then I add another block, add another block. Like I said, this is trivial, and I end up with 6 blocks. That's all integrals are doing, is telling you, it's like adding them up for you, telling you how much have I accumulated left to right. Okay. And so here's the proper symbols for it. The Leibniz notation. Impulse is change in momentum, which is the time from 0 is the initial time to 6 seconds is the final time. My function was really simple. It was simply 1 newtons. It was a constant function, and I did it over dt. Remember, if it's work, it'd be done over dx, and that equals 6 Newton dot seconds, which is that last column. Notice it's not all the add up, it's just this last column. Okay, so now let's get more complicated, and then we're going to torque. So now for a variable force, I'm going to show what happens when the force goes up as you go. So this time, this is the force versus time again. I think we're doing time again. Yeah, so it's force versus time, right? Or is it force versus position? Oh, well, that's my function now. All right. And I'm going to plot how that function now is growing, the rate at which that function is growing. So in the back row, I'm starting to say, okay, like in the first second, I had 1 Newton, but in the second now I have a total of 3 Newtons. See, so we're at 2, but I've accumulated 3. Now let's go to the next one. And if I had the blocks, this is a new thing for me, but I'll have students that have to, I'll make them show me what's happening on that third row. So here on this next one, here I'm just telling you, which is terrible, but it's all I can do. On this next one, I've had 3 plus 3 more. So now I've accumulated 6 blocks behind it totally. See, because this is showing, the second row is giving me, or it'd be the top thing in a trio. This would be a trio, because this would be a situation where velocity is increasing with time and the position's going up parabolically. Here it's force increasing with time, so energy is going up parabolically. That's why when you do the energy for Hooke's law, it's 1/2 kx squared parabolic. Just try and get some of this stuff. Okay, so then the next one, the next second over, I start adding them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now I'm at 10 blocks tall. Okay, that guy's at 10 blocks tall. Uh-oh, this guy right here. Okay. And this is still fairly simple. And now the next one, now we add on, now we're at 15 blocks tall. Because I'm not just adding things. I'm not just adding an apple and apple. I add 1 apple, then I add 2 apples, then I come add 3 apples, then I come add 4 apples. So it's growing exponentially, the combination of apples, or in this case, the combination of work, which then translates to change in energy. I did this during COVID. I just realized, my wife pointed this out. My son had come back from all this wine. She goes, "Oh my God, we're like winos." My son had just come back from San Diego, where he was the manager of this restaurant. He brought back a bunch of the wine because it was just he's a wine rep too. So he brought us all this wine. So it looks like but we weren't. I'm not a big wine guy anyway. All right, so here in the last one now, we add 6 more, and now we got this huge skyscraper, 21. This thing is 21. I've accumulated 21 blocks. That's all integration is doing for you. It's telling you how many blocks am I accumulating. So the proper notation then would be my change in momentum, 0 to 6 seconds. I'm doing it now. It's time. This is impulse. So it's simply t, right? Time is on the bottom, and it's going up linearly. So it's not like 3t or just up by 1 each time. The time's increasing by 1, and then the force is increasing by 1 for each second. So it's not like 2t. Imagine 2t, 3t. This thing's going to get outrageous. End up with 18 Newton dot seconds. You go, wait a minute. I thought it was 21. What's going on? This tells me that threw me off at first. This tells me it's 18, but when I count my blocks, I get 21. Now, somebody tell me why is it off? Took me a minute to figure this one out. Why isn't it the same? Math tells me it should be 18 blocks, but the blocks tell me it's 21 blocks. And my hint is it has to do with pixelation. Anybody want to try it? Wait, hold on. In case you're talking. No, you're not talking. Okay. Anybody want to give it a try? It took me a minute myself. But here's the reason. We're highly pixelated. So if you look at these, when you take out the ones that shouldn't be in there, and you subtract those, you get 18. All right. That's the reason, because the pixelation was our problem. So there it is from a long shot. There it is from kind of down below to kind of emphasize how tall it's getting. And then there we have the, you have the linear, you have the line, and then here you have a line with the slope, then you have parabolic. Okay, so that's what I was trying to get at you. When we're talking about work, we're talking about integrals. But normally now we would do a couple of sheets on it, but it's our last episode. So we're throwing everything in there. Torque. Now I do want to try and work a torque problem with you. At least we'll do something like that. Okay, so here's an introduction to torque. Torque is it's like work in some ways where it's the same units, it's Newton meters. Torque is a force times a distance, but remember, in work, it's force acting through a distance. With torque, it's force acting at a distance. So for torque situation, if I'm trying to say turn something, this would be my force. This would be my pivot point, right? We make the pivot point yellow. I always make it a yellow triangle. I don't know why, just years of tradition. So the pivot point, or sometimes called the axis of rotation, is here. And this is what's called not the moment arm. This is simply the pointer. That's R. It may or may not be the moment arm. We'll get to that in a minute. So torque is not the dot product like work is. Dot products give you scalars. They give you energy in this case, and that's a big deal, but energy is not in one direction. Energy is omnidirectional. Energy radiates. And so you cannot say that energy is a vector. People think, well, vectors are superior to scalars, and I may be guilty of saying that before, but not really, because energy is superior to force, right? All right, so a couple of examples. If the R and the force, if the radius from where the pivot is to the force is perpendicular, that is a moment arm. I call it a true moment arm, TMR. But a lot of times the force is at an angle, and so you have to do this line of action, which is we've talked about line of action since September, but that's a dashed line that goes forever and ever. And then the moment arm, the definition of a moment arm is it starts at the pivot and drops perpendicular to the moment arm. Okay, so every machine you're ever going to work with, if you're working with tools, you use torque every day. This is a pretty big deal. So I have a couple of examples here where I'm applying. In this case, you can apply more than one torque. Like say it's a huge wrench, and we were looking at we were watching some Ice Road movie with Liam Neeson last night, and there was one scene he has this big wrench, and he's trying to turn this thing, and he's got both hands on it. And I said, hey, 2 torques, that's a great example. My wife just ignored me as usual. But this would be a situation where you have 2 torques acting on a pivot, all right? And you could extend these. In fact, I do here. You extend those out, and you get the 2. These are the 2 true moment arms. And you can read this. This is on an equation sheet. So that's true moment arm 1. There's true moment arm 2. Now, someone like Mike Babb, he won't call it the true moment arm. He'll just call it the moment, which is cool. I get it. He works with machines all the time, so it's the moment. But I'm a purist, and I want to distinguish the true moment or true lever arm. It's commonly called lever arm to the radial distance. I call that the pointer. Okay. So this last sheet I have, this is a lot of times this is the last sheet of the year that we get to. And so we kind of got to it on a roundabout way. Down to 11 minutes. I'll go as fast as I can. If I go over, I go over. Well, it'd be cool if we could sit and work this whole thing out. I've put the key. I will. Oh, I'm adding to the key. So I'm going to add I'm beefing up the key. So I'm going to put the beefed up key on probably tonight or tomorrow night on the Facebook group. And by the way, that Facebook group, now that you're members, you'll be members for life. I'm not going, like most Facebook groups, I don't really kill them, but they kind of die on their own because, the class departs. Right now I have 212 people on that Facebook group, and a lot of them are physics teachers, ex-students, engineers, physics professors. Um, there's my family's on there too, because it's sort of where if they don't know what I'm doing, they can look on there. But that's where I spend my time. But it's sort of it's a physics show. It's like a three-ring circus, and we'll continue to add stuff on there. I'm not sure what to do in the fall when I have a new crop of kids that don't know any physics. You knew some physics, they don't know any. And I don't know whether to put them on there or start a whole new one, but I don't know. I'll ask you Thursday during our lunch. All right, so here we are on torque, and we're pretty much going to end our thing with this torque. Oh, we'll end it with statics. I don't know if we'll get to matrices. The last couple are matrices, which is pretty cool. It's like cross products versus dot products. Anyway, so let's start off with a basic torque problem. Now, here's one I would like you to try and work on a piece of paper. So I'll leave this up here. I'm going to hit pause so we're not wasting their time, those that are watching, and we'll come back in a second. But if you're watching this, I'm going to hit pause now and pause recording. Okay, I'm came back on for a second because I want to the studio audience there. They're drawing this out. We're going to talk about it, and we'll talk about it with you guys in the recording as well. But those numbers, that 20 and 37, when you first looked at it on your pause screen, I'm sure it kind of you were going, what's going on? So I fixed that. Okay, I'm going back to pausing again. Now, before we start working this problem, I have some demonstrations that I'm rushing around and not. Let me stop the sharing. Okay, so I have some demonstrations. I don't want to destroy my iPad. Let's get this out the way here. But we pass this around the room, and we do something called Torque Man and Torque Woman. I had to stop because Daniel Huffaker busted his shoulder. He was the #1 tennis player, and yes, about 2 weeks before the tournament, and so the coach never forgave me. But he was Torque Man. I mean, he became Torque Man, but he messed his rotator cuff up. So if I have this guy here, you can see it. All it is a very simple little. It's kind of a cool thing. So we can make a little kit here. So you have a little T, and then you have a ring, and on there you put a weight. Okay, and then if this is torque, right? So if you hold this and pass this around the room, kids, say how far out can you go? Well, any kid can do this, but now you start moving this thing out, and you got to hold it, and then you keep moving it out. Okay, and you got to lift that up, and you find out really quick that torque is a big deal. I mean, I'm kind of, good grief, I'm weak. See, and with Torque Man, you had to hold it with one arm. That's not this. It was a different deal. That's probably stuck in a box somewhere at school. So that kind of really gives you a feel for the torque because it's going up. If I double the length, I didn't change the weight, but if I double the length, that doubles the torque because it's R times F, right? R cross F. So R plays the radius, how far away it is, the lever arm plays a huge role. If it goes out 4 times, all of a sudden, if it was, if I can maybe handle 100 foot-pounds of torque, but maybe not. Let's say 50 foot-pounds of torque. But if I go 4 times, now it's 200 foot-pounds of torque. You see what I'm saying? So it's not just the added weight. Okay, that's weird. All right. It's not just the added weight. It's what am I doing? Lost my mind. Okay, so it's not just the added weight. It's also the added moment arm. All right. So now back to this problem. And let me share again. And by the way, this problem is I put together a Silent Help video, and this is already in the comments. There's a preview now on the Facebook group. There's a preview for the episode, and I put a lot of the references in the preview already. So there's a Silent Help video of me. It's about a 2-minute video of me going through this one. Okay, we're down to just a few minutes, so we'll at least get it started, and then I'll refer you to that help video. Okay, so let's at least set this thing up. So what I do is first I gotta find my pivot point. That's the point that's not moving. That's the point that it's rotating about, the axis of rotation. Well, it's not the spinner, it's the hand. Okay, let's say you're just fishing with one hand. So there's my yellow triangle. Once I establish that, everything from Circular World, you always have to establish the middle. You always have to establish what's the center, and then everything revolves around that. Everything is in reference to that. Okay. Then I'm going to go ahead and do the R. The R is the pointer. The R stands at the pivot and points and says, there it is, there it is. It points to where the force is acting. So here we go. Pivot comes up. There's the R. R says, there it is. All right. Then notice that's not the moment arm. That's not the true moment arm. That is simply the pointer. And then we draw the force. The force is this fish, and he's pulling this way. Change colors here. So there's my force. Now, whenever you draw that force, and that's 100 newtons, okay, then you also go ahead, while you got your ruler there, you go ahead and draw your line of action. The old LOA, right? And line of action can go all the way off the page. You can keep going on the table, on the floor. It goes as far as it's got to go, okay? By definition, it's infinite. It's just a line of action. Okay. We use it all the time in physics for construction, like in head to tail. But here we're using it to kind of get a feel for what's going on. So now I have the R, I have the line of action, and now I'm going to draw the true moment arm. True moment arm, I'll make it purple. True moment arm goes from the pivot perpendicular to the line of action. Like that. So that has to be a right triangle. Okay. Next thing you do is you color that in. You color in the right triangle that's formed, because that's the right triangle you're going to work with. Now the angle that is in the vertex of the line of action and the R, that is your, let's go black, that is your phi. I don't put theta. We use theta for work, for cosine. We use this phi for sine, okay? So now I can find what the torque is. And I go through all this on the Silent Help video in the comments. So torque, it is a vector. I'm obviously going to run over time. It's okay. You guys can, if you feel like you got to go, but stick around. This is my last episode. I've got to finish this, and then I got to look at little statics, and then that ought to probably do it. So we're getting close. So torque, I'll go the fast route. So torque equals R cross F. That's called a vector product, and cross product for math. Physics is called a vector product. Another way of saying that is torque equals the absolute value of R, the absolute value of F, times sine of phi. Remember that work was absolute value of force times absolute value of delta S times cosine of the angle. With torque, it's the sine of the angle. Okay, because I want remember that we said that work is dot products are how much two vectors are agreeing with each other. Cross products is how much two vectors are disagreeing with each other. Okay, if you think of it that way. In a cross product, you're trying to twist. One vector is trying to twist the other vector. That's in a cross product. In a work product, they're working together to make energy. But in cross product, they are fighting each other to make rotation. Okay. The fish is fighting you. So here, the R, it says is 2 meters. Let's quickly get an answer here. 2 meters. The force of the fish is 100 newtons. And sine of the angle, let's add those up, 57 degrees. Okay. And then we get a torque. What do we get? What do we get? 166, I think. I got it right here. My final product, 168. So 168, oops, 168 Newton meters. 168 Newton meters, which I know is confusing because it's just like work, but you got to realize you got to read the room. You got to know what you're doing. And so 168 Newton meters of twist. Now, question is that positive or negative? Remember that we said that anything going clockwise is negative. So this is going to give me a negative torque. But the question is, where on this drawing would I show that negative torqueness? And you show it, torque, it's a vector. If I do a right-hand rule, if you put your fingers, hold on, let me stop sharing for a second. So on right-hand rule, if I put my fingers in the direction of the R and cross them into the direction of the force, my thumb is the direction of the torque. So like say R was going this way and force was going this way, then it's going to be up. That's a positive torque. But in our case, going back to this, let's go back to the sharing here. In our case, the R is going out, the force is going down, and so I can see my hand here, but my thumb is going down. So that's the negative torque. So I show that, I always emphasize it real big, but you show that right there at the pivot. So it's a big X. We've done that before. Big X goes right there. That's showing, that's the, okay. So there's the final, that's the final screenshot of that Silent Help video, which I've now lost forever. I did explain everything, wiped out everything for some crazy reason today, but I did keep at least a YouTube video of it. And then let's look at one more thing, and that's statics. And lots as we end the year on statics. So statics is this idea of balance. And we said, well, we've done this, right? Remember truss? But this is different. This is more complicated. I still don't understand how they balanced 4 golf balls on top of each other. But here's one of those things that, you know, physics level 99. But all of these are static. I mean, if you take all the forces up and down and sideways and all the torques and all those add up to 0, then it's not only is it equilibrium, it's not moving. Okay, that's considered statics. So like I say, you'll take a course in college, the entire semester, you'll be studying things that don't move. Sounds boring, but it was one of my favorite courses in engineering because it just, then we had dynamics and oh my gosh, it got hard again. All this acceleration and jerk. And but anyway, statics is cool because we set everything equal to 0. Here's like in these big barges, these big, you know, cross Atlantic, you know, like the person that got the Evergreen, right? They got stuck in the Suez. Here's one where when they're loading those containers, they're very concerned with statics. If you have a lot of, if you got, you know, if you're, if these are full of lead over here and these are full of cotton, we got a problem. So they're constantly having to weigh everything, keep everything balanced, know how far it is from this, you know, the pivot point, how far away is that? Because it's going to cause a different torque. And so your summation of torque has to be 0 or out there and that you get a good wind gust going and it'll just exacerbate it and the whole thing will go in the ocean, which has happened. Once it gets going, then and like say a wind comes up and a big wave and knocks off 5 of those, all of a sudden we're out of balance and then it even gets worse. So this whole thing can capsize. I would not want to be on one of those things. But all of the forces in the X, Y, and Z have to add up to 0. And all the torques have to add up to 0. So there's always computer programs they use when they're loading these things up. This is the last problem of the year. And I did a silent help video on this. It got lost, but at least I saved the YouTube of it. And so we're not going to work it. We're already over time. But for a few minutes here, I just want to show it to you. This is the typical kind of problem you'll see in AP Physics, perhaps even on an AP Physics exam, where you have to figure out, there's 4 unknowns here. I don't know what the this is, really 3 unknowns. I don't know this angle, and I don't know how far away it's got to be. I say 4 because I've got to find the X and the Y of that right triangle. So that's sort of your approach. I'm going to walk you through it. And then if you're interested, there's like a 2-minute video here. But here we go. I'll blow this up so we can kind of speed through it. That's why I said 4 unknowns. There's 2 components to that vector. So the first thing you do is you turn every vector that's at an angle. I don't know if I've told you this, maybe back in September, that a vector at an angle is the hypotenuse of a right triangle. I think that's now the 1000th time I've told you that this year. But you turn that into a right triangle, so I always color mine in. So we have 3 right triangles here. Then the 250 newtons is acting, and I guess this is not down. This is a map view, because if it was down, we'd have a weight. There's not a map view, so it's a top view. And by the way, if you want to work some of these statics problems, it'll really do you benefit. This whole sheet, I'll post the key to it by tomorrow, and it's got every problem on this sheet's good. Okay, so you arbitrarily choose. It matters not where you put the pivot if it's not rotating, right? It can be anywhere. It's arbitrary. So you always put the pivot in a spot. I mean, you could put the pivot right, here in the middle, which would be dumb. You didn't help yourself at all. You made your life harder. So you always put the pivot in a place where you can eliminate something. So if I put the pivot right here, I can eliminate the torque. I can't eliminate the force, but I can eliminate the torque from that 380 newtons. Not because the force went away, but the X went away, the R went away, okay? All right, so now you go through this methodically, and first you do all the forces in the X. Those all have to equal 0. So let's get rid of this guy, kill him. And that's my equations for the X, all right? Cosine. There's nothing from the 250 newtons. And so we have cosine. Oh, okay, good. Yeah, there's 3 things, but I don't know what fx is. I know what this 380 cosine 40 is. I can get that. 450 cosine, and those are both positive. I'm going to say, to the right, it's positive, the standard. And then it's not moving, so there's no direction of motion. And then I take minus. I know this thing's going back. That equals 0. So I find my fx. I find one of my 4 unknowns is 369 newtons. Okay, now I go to the y, do the same thing. So in the y, let's uncover that. So in the y direction, I'm making that blue. I have 380 sine 40, right? Because cosine for x, sine for y, minus 250. Now I am going to use this. Minus 450 sine 80, okay? Plus, this is up, so I made it plus fy. And that equals 449. So now I have 2 unknowns. And now I can go ahead and also I can find the angle. So give me my 3rd unknown, inverse tangent. I did it somewhere here. Inverse tangent would be the angle there. That's not hard. But the problem is, and a lot of students will get that far in a test and they just give up because they don't really go into using the torque. I've got to find that X right there. And there's no way that summation of forces is going to find that X, only torque. So, here, I think over here is where that's where I found the angle be 50.6 degrees. So now we got to go through and do torque and get rid of all that. And this is the torque work, right? R times F times sine of phi, and also clockwise is negative torque, counterclockwise is positive torque. That's why up here I put negative torque, positive torque. And there's no torque from the 380 because that's right at the pivot. So I plug these in, being careful. That last one, the pivot arm, the first one is 2 meters. That's the R. The next one is 7 meters. And that the next one is 7 plus X meters. Notice I'm using the perpendicular component on the 380. On the 380, I'm using the perpendicular. On the 450, I'm using the well, the 380 I'm not using, but the 250 I'm using, it is perpendicular. On the 450, I'm using the perpendicular component. And on that new one that I now know is 449, I used it, 7 plus X. So now it's a matter of algebra 1 solving for X, and I get 1.02 meters. Whew. And that's a good old static problem. And of course, in AP Physics in chapter 12, they're going to start to make this more complicated. It'll be a non-uniform, it'll be a baseball bat that changes shape. So all that kind of stuff, you need calculus to do it. You need to integrate the mass, how it changes. All right. So this is my final slide for the year. I was reading this the other day. I thought that's pretty much basically physics. Is you're probably wrong. Your goal is just to be less wrong, and that's what I'm hoping that you'll get. You don't be a perfectionist. I mean, if you're a perfectionist in physics, you're gonna have a heart attack. You're gonna go crazy. So you got to drop that. I used to be a perfectionist, but physics fixed me. Okay, now I'm 12 minutes over. So I don't, this may be the last time I see you guys. Hopefully I can see you Thursday. Come for some free pizza, okay? But I don't want you just showing up without letting me know. You got to RSVP because I'm going to buy so much pizza. And so I need you to, if it's just us few guys, I'll buy one pizza and we'll munch. But if it's 10, I got to buy a few pizzas. So try and work your schedule where you can come. I want to give you your certificate, shake your hand, and then have you fill out a little form. If you miss it, then you missed out on the pizza. What can I say? But I'll still have you fill the form out online. So it's been a pleasure. I think it's going to be good. We're going to have a good time in the fall. You were great to come. You're still coming. Here it is, almost July, and I appreciate that. And I do keep attendance, so I'll somehow mark that on the certificate. All right. So hopefully I'll see you Thursday. If not, thank you for coming, and I'll be emailing you a little questionnaire. All right. Bye, guys.
Thanks, Mr. Askey.
Thanks, Sophia.
I can probably show up.
You're saying yes.
Probably.
Okay. We'll take that as a yes then.
Okay.
Okay.
See ya.
All right. See you. Anything from you, Carson? Last thoughts? Okay. See y'all.